So we have seen one algorithm for the minimum cost spanning tree, namely Prim's algorithm. Now look at the other. Let's look at the other strategy we talked about, namely Kruskal's algorithm. Right. So we are looking for a minimum cost spanning tree in a weighted undirected graph. So Prim's algorithm starts with some edge and gradually expands the edge into a tree, whereas Kruskal's algorithm follows the other strategy, which is to order all the edges in ascending order of weight. So it keeps trying edges from smallest to largest, and for every edge, if it can add the edge without violating a tree property, it adds it. Now in the process of adding the edge, it may not actually construct a tree. All it makes sure it doesn't violate the tree property, namely it doesn't produce a cycle. So if we keep adding edges so long as they don't produce cycles, and at the end the claim is we get a minimum cost spanning tree. So here is a kind of high level view of the algorithm. So let the edges be sorted in order E1 to EM. So we start with an empty tree. Right? So again we will keep the tree as a list of edges. And now we are going to scan this in order 1 to M. So let I be the index of the edge to be tried next. Right? So long as we have not yet added n minus 1 edges. Remember that if we add n minus 1 edges and we have a connected graph, it must be a tree. Right? This was one of the various characterizations that we said about trees. Trees have n minus 1 edges, but any connected graph with n minus 1 edges must be a tree. So once we have n minus 1 edges, we can stop. So long as the length of the tree in terms of number of edges is not n minus 1, we have to add some more edges. So we look at the next EI. If EI does not form a cycle when added to T, we append it. And then we look at I plus 1. If it does form a cycle, we just discard it and go ahead. Right? This is all Kruskal's algorithm. It's scanning through all the edges, and until we have formed a tree, it will just keep looking at each edge in turn in ascending order of the weight. And every time if it can add it, if without forming a cycle, it will add it. If it cannot add it without forming a cycle, it will drop it. So let's look at the same example that we saw for Prim's algorithm. So here the smallest edge weight, so remember that we have sorted it in edges. So 5 is the smallest, then 6, then we have 3 of weight 10, then we have 18, then we have 20, and then we have 70. Okay. So now if we pick among these the smallest one, we start with the edge 5. So we first add the edge 5 to our tree. Now the next one is 6, so we add 6 to our tree. Now we have to pick one of the edges labeled 10. We can pick any one. So let's assume that we pick this one. Okay. Now we want to pick another edge labeled 10 because the next two edges are again labeled 10. So supposing we pick this edge labeled 10. Okay. Then this edge labeled 10 forms a cycle. So we cannot add it. So we discard it. So we discard it and go to the next one. So now we pick this one. So we'll throw this away. Right. And now we'll go to this one. And now this one we can add. So now we have finished the 10s, so the next one is 18, but again adding 18 is going to form a cycle. Right? So we discard it, and now we go to the next one, which is this 20. Okay? Now having added 20, then we still are not done because we have still to add enough edges. We have 1, 2, 3, 4, 5 edges, and we need 6 because we have 7 vertices totally. We need n minus 1 edges. So the only edge left is the 70, so we add that and now we are done. Right? So this is the spanning tree formed by Kruskal's algorithm. We actually scanned through all the edges in this particular case, and on the way we dropped a couple of them. Right? So Kruskal's algorithm is also a greedy algorithm. In this case, we don't make so in Prim's algorithm or in Dijkstra's algorithm, we make incremental choices, local choices. At every point, we look at what to do next based on what we know now. Here we make a choice well in advance. We say right at the beginning, let us sort all the edges and do it in that order. Okay? And again, it is not clear why doing it in this particular order, which is decided right at the beginning, gives us overall an optimum solution. So once again, we will use the same result that we use for Prim's algorithm, this minimum separator lemma. So recall what the lemma said. It said that if we take our set of vertices and separate out into two non-empty groups, U and W, and if we take the smallest edge, now the graph is connected, so there must be an edge connecting these two. If we take the smallest edge which connects the two parts together, then this edge must be there in every spanning tree, every minimum cost spanning tree. Right? This is what the lemma said. Okay. So now in Kruskal's algorithm, unlike in Prim's algorithm, okay, at the intermediate stages we don't have a tree. We just have a collection of components. So we will have in our overall graph, we'll have some vertices which are connected here, then maybe some other vertex there, and then another part there, and so on. Because as we add edges, it just connects them. Okay, and now whenever we add an edge in general, it will take two currently different components and connect them. We can't add an edge within a component because each component is like a tree. So adding an edge in a tree, remember, forms a cycle, right? So this won't happen. What we will do is we will add edges across, right? So this is the strategy of Kruskal's thing. Now, what we therefore know is that whenever we add an edge, okay, its two endpoints are in disjoint components. So in terms of using the lemma, let us call capital U to be the component containing one endpoint of the edge, and capital W to be the rest, okay, whatever is outside this. So this is whatever is outside component, right? So we have U and whatever it is connected to. So this is my set U, and then I have the rest of the vertices. So U is connected at this point to something in a different component, but that and all the other components is what I will call W. Right? So now what do we know? This is the first time that we are trying to connect U to V. U to V have not been connected so far, but we have been looking at edges in ascending order of weight. So if we look at all the edges, so this current edge we have called EJ, right? So if we look at all the edges E1 to EJ minus 1, none of them connected U to V, or the component connecting U, because had it connected the component connecting U to the component containing U to the component containing V, then we wouldn't be adding this edge. This edge would form a cycle. So this is the first edge that we can use to connect these two, means that no edge we have seen so far connects these two. Okay, so putting all this together, this is the smallest edge which connects capital U to something outside capital U. Right? And since this is the smallest edge, the lemma tells us this must be in the tree, and therefore Kruskal's idea of including this in the tree is sound. Right? This is an edge which must be in the tree. So every edge that Kruskal's algorithm adds is actually a valid edge justified by the minimum separating lemma. So now we have to just decide how to keep track of this property of forming a cycle. Remember that whenever we add an edge, we must first check if it forms a cycle, and if it doesn't form a cycle, we must include it. Right? So the easiest way to check that the edge doesn't form a cycle is to keep track of the components. If the edge is incident on two different components, that is one endpoint of the edge is in one component and one endpoint of the edge is in the other component, then inductively each component is a tree, and therefore these two trees are disjoint, and therefore the new edge doesn't form a cycle. If the two endpoints are in the same component, then it will form a cycle. Okay? So keeping track of whether or not a new edge forms a cycle is equivalent to keeping track of components. So how do we keep track of components? Well, we can basically label the components by numbers, and since we have n vertices and initially they are all n independent vertices with no edges in the initial starting point of Kruskal's algorithm, everything is disconnected. So initially we have n vertices, n components. The most natural thing to do is say that each vertex I belongs to a component called I. Now I can add an edge uv if the component of u is different from the component of v. Okay? And if the component u is different from component of v, what happens after this is the two components become the same. So I have to somehow merge the two components. In other words, I have to give them the same label. Right? So this is now a detailed explanation of the algorithm. So as before, we let E1 to EM be the edges sorted by weight. Now initially we say that every vertex 1 to n is in its own component. For every j in 1 to n, component of j is j. So 1 is in component 1, 2 is in component 2, and so on. Now we start off with an empty set of edges, right? And now we are going to run through, as we said before, these edges in ascending order. So we have the index pointing to the first edge in my sorted array. So this is my index. So long as we have not added n-1 edges, we look at the ith edge in this sorted order. It is of some u to v. If the current component of u is different from the current component of v, then we are sure that the edge ei does not form a cycle. So we add it to our tree, right? And now we have to do this merging of components. Now what is the component of a vertex? It's just a number. So for every j in our set, now the problem is that these components could have been merged earlier. So component of u could contain other vertices, component of v could contain other vertices, and all of them must now be given the same component number so that they're all in the same component. So I have no choice but to scan every j in my set of vertices, and whenever such a j has the same component as v, I reset its component to u. Okay, so after this, everything which has the same component number as V has got the same component number as U. So therefore, effectively, the two components have been merged into one component, all labeled by the value component of U. Right? So this is Kruskal's algorithm. It just says keep considering edges, and if they connect different components, add them and merge the components. If they don't connect different components, it will form a loop, so just throw it away. So what is the complexity? Well, the first step in Kruskal's algorithm requires us to sort the edges. So we know that we can sort m edges in m log m time. But m is at most n squared. Okay, so log m will be 2 times log n. Right? So order of log m is the same as order of log n. So I can also write this as m log n. Okay, so this will be it's just another way of writing this. So the sorting takes m log n time. Now we have an outer loop. Okay, so this loop which runs here in general runs through all the edges in this list, because it could very well be that for some reason I have to go all the way and only the last one forms a tree. Okay, even in the example we saw, the largest edge has to be included in the tree because it's the only one that connects us to some particular vertex. So we have an outer loop which runs m times. Now among these m times, okay, we will update the components for each edge we add. That will happen only n minus 1 times. Right? But when we update the component, that's when we have a problem, because we have to scan through all the vertices in order to change the component number. So each update of the component, each merging component step takes order n time, and this itself happens n minus 1 times, because we have to keep doing it each time we add an edge to our tree. And there are going to be exactly n minus 1 edges. So we have n minus 1 updates. Okay, and each update takes order n times. So we have an overall complexity of order n square. Okay. Now remember that in Prim's algorithm, n square was the worst case, and then we said with a better data structure we could bring it down to m plus n log n. So what can we do here? So let's look at the problem. Okay, the problem is basically this labeling strategy. Okay. Now when we label the components and do this linear scan, we are spending order n time in order to merge components. So we'll find, just like we can use a heap for Dijkstra's algorithm and Prim's algorithm to find the minimum vertex to be added quicker and to update the distances, here we will find that what we need to do is maintain this component structure. Okay? So assume that we want to deal with a set V which is broken up into different components. Right? So it has components at any given time, say called A, B, C, D, E. And then you have individual elements which belong to these components. So some of them have many, some of them have one, and so on. So one of the things we want to do is, given the name of a vertex V, we want to ask which component does it belong to. Okay, so this is called find. Okay, given V, find the component containing V. The other thing is, given two vertices, supposing I'm given a U and a V, it will say merge these two. Okay, so take these two components and give them the same name. Right? So either call them all C or call them all D. Right? So this is called union. Okay, so union doesn't take the components, it takes two representatives, one representative from one component, one representative from the other component, and then says merge everything which is in the component of U with everything in the component of V. And these are the two operations obviously that we do in Kruskal. Right? Find V is what we, if we have an edge UV, right, to check if they are the same component, we find the component of U, find the component of V. If they are the same, that means they are in the same component. If they are different, they are in different components, and we can add this edge. Now if we add the edge, then we have to do union UV. Right? So these are precisely the two operations, and we will find that there is this data structure which is called union find because of these two operations, which can actually do this efficiently. And efficiently means what? It means it can eliminate this n squared thing and bring everything down to the cost of m log n. Now remember that this we need to sort. Right? So our first step was to sort the edges. So Kruskal's algorithm starts by sorting the edges. So m log n is something which we need to do anyway to sort the edges. In addition, these essentially this updates as in a heap, the updates to this union find will give us is actually log n. And remember that there are going to be these updates are happening in this iterative loop. So we'll actually get something similar to this Prim's algorithm complexity.